arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold protectin.
So today we're going to work on a lab to determine the heat capacity or the specific heat capacity of a metal. So the first thing we're going to do is get the mass of our sample of zinc, which is 55.65 grams. Now I'm going to take the sample of zinc and put it in a beaker of boiling water in the fume hood. And we'll let it sit there. The temperature is 99.3 degrees. So we'll record that. Here we have our simple calorimeter. It's a couple styrofoam cups with a lid, and they're just sitting in a beaker for stability. I'm going to put 25 milliliters of water in and record the temperature. So this will be the cool water in the calorimeter, and that is 22.0 degrees. So what we're going to do now is we're going to move the zinc metal into the calorimeter. And what will happen is the metal will undergo an exothermic process, releasing heat, which will be absorbed by the water. So for the water, this will be an endothermic. And then we'll do a little bit with the law of conservation of energy and our heat capacity equation and see how well we can do calculating it. So I'm going to move this over here so that I don't carry the piece of metal all the way around the room where it would cool off. So I'm going to take this out, drop it in the water, wait a couple seconds, and take the temperature. And I'll know I'm done when the temperature stops changing. So the temperature's still going up. And one thing I want to keep in mind is, even though I'm only taking the temperature of the water, the metal and the water have the same temperature. It's a concept known as thermal equilibrium. So that's 35.9 degrees. So we have all of our data now. So the first thing we want to do is calculate delta T for the metal. And we're just going to use the absolute value, which will make our calculations a little easier. So the metal started out at 99.3 degrees. And it ended up at 35.9. So that means that the metal cooled down (63.4 degrees). The water in the calorimeter started out at 22 degrees and warmed up to 35.9, so that went up by 13.9 degrees. So you'll notice that the metal underwent a much larger temperature change than the water. Now we're going to come over, and in step 10, we're going to calculate the amount of heat that the water absorbed. And you might have seen this with either Q or delta H, and some teachers use one over the other. They're both fine. So this is going to be Q equals the mass of the water, which is 25 grams, times the heat capacity of water, which is given to us, and it's 4.18 joules per gram degree. It's not a number we'd expect you to memorize. And the temperature change of the water is 13.9 degrees. So I'm going to get joules, a unit of energy, and I'm going to get 1,450 joules if I go to 3 significant figures. And I can do that because that should be. Now, if I know the law of conservation of energy, that means that all the energy the water absorbed had to come from somewhere. And the somewhere was the metal. So the metal released or lost or gave off the exact same amount. So we just write conservation of energy. And that's not the most obvious thing sometimes, so you might want to take a second, make sure it sinks in. Now we're going to take this same equation, only we know the amount of heat, but we don't know the heat capacity. So now we're going to say 1450 joules equals the mass of the metal was 55.65 grams. The heat capacity of the metal we don't know, and the temperature change for the metal was 63.4 degrees. So we actually have a lot of numbers kind of floating around the page. So you want to be really careful to label everything and use units. So if we solve that, we're going to get 1450 divided by 55.65. 0.41 joules per gram degree Celsius. The accepted value, the correct value, is 0.39 joules per gram degree Celsius. So that's pretty close. Yeah, we're really pleased with ourselves for getting that, aren't we, Miss Valatek? Because
Most certainly.
yeah, let's chalk that up to excellence in teaching, shall we? And then for percent error, you have the formula. Again, we don't want you to memorize these formulas, but you would go 0.41 minus 0.39 divided by 0.39 times 100, and you'll get 5%. Which is pretty darn close. So we've already set up the calorimeter like we did in the first sample. So that's got its 25 milliliters of water, and it's over there ready to go. First sample now, and these are the ones you're going to be calculating. Here's a sample of lead. It has a mass of 58.01 grams. So you're going to have to write that down in your data table. I'm going to put the lead in the water. Get the temperature of the hot water. It'll be boiling soon. And the temperature of my calorimeter water is 22.0 degrees again. So this is going to be heated up close to 100 degrees, boiling water. Then we'll do the same transfer we did last time, and then you'll do the calculations. Right. So our water is 99.6 degrees, which is also the temperature of the metal. I'm going to take this, transfer it from here to here, let it equilibrate or reach a common temperature, and measure the temperature. So remember, the water in the calorimeter was 22.0 degrees when we started. So this is 26.2 degrees. So in this case, the metal cooled off a lot and the water didn't heat up very much, and we'll see what that means when we do our heat capacity. So now you have all the data to do your lead calculation. The calorimeter is set up again, still using tap water, 22 degrees. The copper sample we're doing for the second trial you'll calculate is 58.02 grams. I'm going to transfer this in here, let it sit for a few minutes in the boiling water. And now that it's had plenty of time to reach the same temperature as the water, which in this case is reading 99.3 degrees. So I'm going to transfer the metal into the calorimeter, let it equilibrate, wait for the temperature to stop changing. and we're getting 38.6 degrees. So now you have all the data to calculate the heat capacity of copper.